Hello everyone! In this seminar, I will introduce you to the overview and usage of DOE and Simulation Manager. These are the contents of today's seminar. In the first and second chapters, DOE Introduction and how to use DOE will be introduced. We will talk about what the Simulation Manager is and DOE speed improvement using Simulation Manager in the latter chapters. Finally, we will draw a conclusion and wrap it up. First, let me introduce you to DOE. The first to explain is the definition of a DOE. The general meaning of a DOE is how to plan experiments to solve problems. It is also called design of an experiment in which the maximum information can be obtained from the minimum number of experiments. From the design point of view, it is to predict the actual effect on the product in advance according to the value of the design factor in the early stage or upper stage of product development. The purposes of a DOE are as follows. The DOE's purpose is to determine whether changes in the design variables required for the design of a product have a significant effect. In other words, it is to understand how changes in design variables affect product performances. Another purpose of a DOE is to obtain the optimal value of the design variables by identifying the performances through the changes in these design variables. If so, what industries use DOE? DOE can be applied in our industries that require design, such as automotive, robotics, industrial machinery, and agriculture machinery. So, let's take a look at the advantages of RecurDyn DOE. The first advantage is that you can set the DOE levels via intuitive UI. Easy design, variable creation, and performance index settings are also another advantages. Thirdly, the analysis with multiple design variables and performance indices are possible. In the DOE dialog box, there are sections to set the minimum and maximum values, and you can intuitively see each design variable and the number of design variables. And the simultaneous analysis of the DOE analysis cases is possible using Simulation Manager. The DOE analysis via Simulation Manager, which will be explained in more detail later, enables a significant analysis speed improvement. In addition, RecurDyn DOE provides various DOE methods. The various method options allow the convenience of selecting the desired method for users. Each of the 6 items will be explained in more detail later. From now on, let me introduce you to the overall work process of RecurDyn DOE. First, set up your design variables. Create PI, which is a performance index using expression that extracts analysis results. After that, set the level of each variable in the DOE dialog box. After a DOE table is generated, an analysis case is created. After checking the list of performance index, set the analysis time and the step size for simulation. Perform a DOE analysis. When the analysis is complete, review the results. If the modification of a variable range or the change of a variable types is needed, you can proceed with the DOE process again. Finally, after reviewing the results, the work process of RecurDyn DOE is done. When performing the basic DOE analysis, the analysis cases are simulated one by one in the RecurDyn UI. However, the newly developed Simulation Manager makes it possible to perform multiple simultaneous simulations. It is now possible to perform much faster and more efficient DOE analysis. The Simulation Manager will be explained in more detail later. In this chapter, let me introduce you the basics of how to use DOE. Now, I will explain how to use DOE with a simple example. Let me proceed with modeling in the order of the work process as described on the previous page. The example model is a pinball model, as you can see here. To briefly explain the model's situation, ball 1 is pushed by spring. After ball 1 makes contact with ball 2 passes through the obstacle on the right and makes contact with ball 3. The purpose of this model is to understand the characteristics of a spring. First, set free length and stiffness as design variables among spring characteristics. The performance indices are to understand the displacement of ball 2 and the contact force between ball 1 and ball 2. First, let's check the overall behavior of this model as an analysis result. As you see here, the analysis results show that ball 2 overcomes the obstacles through contact with ball 1 and makes contact with ball 3. Now, let's proceed with the DOE modeling to check the performance indices according to the changes in spring's free length and stiffness. First, set the design variables. To define the design variable, it is necessary to define the parameter value first. Define the spring's stiffness and free length in the parameter value list as shown in the figure. For reference, the PV is located in the parameter group of the sub-entity tab. Open the Properties dialog box of a spring and input the previously defined PVs in the dialog box. Here is a video that shows how to define design variables using PVs. After clicking the DV button, click the Create button. Specify the names of DVs and find and select the PVs corresponding to these DVs. Click the OK button and proceed with the same task for the other design variables. For reference, the range for design variables will be defined later in the DOE dialog box. So, for now, leave them as defaults. The second step is to define the performance index. First, create expressions to be used as a performance index. For reference, expression is located in the expression group of the sub-entity tab. Click the expression button to open the expression list dialog box. Click the Create button, then the expression dialog box appears. Define the displacement of ball 2 and the contact force between ball 1 and ball 2 as expressions. Let me briefly explain each expression. The displacement of ball 2 can be measured through the dx function, and the contact force in the desired direction can be obtained through the contact function. Now that expression has been created, the performance index can be defined. Not only expression, but also scope and process net can be used as a performance index. In the lower part of the performance index list dialog box, you can select the type option. After selecting the type, click the Add button to display the setting dialog box for the selected type. This is the performance index dialog box that appears when expression is selected among the PI types. You can set the PI using the created expression. Expression can be selected by clicking the EL button. When selecting scope type, you can set the PI using the created scope. Lastly, this shows the PI dialog box when selecting process net type. You can set the PI with the previously created DLL file using processnet's VSTA, General, or Python. In addition, in the case of expression and scope, treatment can be set. Various factors such as maximum and minimum values can be set for treatment. In this example, the maximum value will be set. Here is a video representing how to define performance indices using the defined expressions. First, click the PI icon and then the Add button since the type is already set to expression. Then, name the PI and click the EL button to select the expression used as performance index. Set the treatment and click the OK button. Repeat the same process for the other performance indices. Now, the PI definition is complete. In the third step, I will talk about the settings for the DOE analysis level. When clicking the DOE button shown on the left, the DOE dialog box where you can set the DOE appears. For reference, DOE is located in the Simulation Type group of the Analysis tab. Let me briefly explain the elements you can see in this DOE dialog box. If the DOEs have been created already, they are automatically listed up and displayed. And you need to set LB, UB, and number points to be used in DOE instead of the default values. To do this, click the Tool button marked with a red box. Then, the Tool dialog box will appear where the details of the DOE values can be set. LB is the minimum level value, and UB is the maximum level value. And the number of design variables, which is number points, is defined by the user. After that, click the Generate button, then a table is automatically created at the bottom of the Tool dialog box. If you click the OK button, you can see that the values of LB, UB, and number points are automatically updated as shown. Next, let me talk about how to set the DOE method and how to create a DOE table that actually defines the analysis cases. First, here's the definition of the DOE method. As shown on the right, users can select the DOE method option, and RecurDyn provides a total of 6 methods. I'll briefly explain each DOE method. The first is a full factorial design, which is a method to compute every case. This method is a two-level full factorial design, which is used only when and the values are used. Two-level Plackett-Berman design is used when it is necessary to identify the major influencing factors in the early stage of the experimental phase. In the case of the central composite design method, it is used when the analysis needs to consider the intermediate value of the experiment also. Box-Beacon design is used when our DOE factors have maximum or minimum values, or when the experimental cost is too high, or the experiment itself is practically impossible. Lastly, Latin hypercube sampling is random sampling, which defines the number of cases as specified in required runs. In this seminar, detailed explanation of methods will be omitted. For more detailed descriptions of all methods, refer to the RecurDyn manual. Now, let me talk about how to create a DOE table. If you select the Append option, the DOE cases are added to the existing table. If you select the New option, the existing table is deleted and a new DOE table is created. After selecting either option, click the Create Table with the DOE button to create a DOE table. You can see that a DOE table with 100 cases are created since 10 cases are set each for 2 DOE items. For reference, the full factorial design option was selected as a DOE method for this DOE table. Next, check the previously defined performance indices. When looking through the Performance Index tab of the DOE dialog box, you can check the output type, output target, and treatment of items created with PI. In the next step, let me explain the Simulation tab for both the settings and execution of the DOE simulation. First, you can set the simulation type and step in the area marked with a red box. You can set the exception handling for interrupted trial during DOE simulation in the red box on the right. If the when simulation fails, continue with the next DOE trial option is checked. The on failure set PIs to is activated, allowing the user to put the value to be set to the performance index when the simulation fails. This section is to determine whether to display DOE analysis results and generate result data. If you click the simulation button, the analysis is performed sequentially as specified in number of trials. The bottom part is related to the simulation manager, which will be explained later. As a brief explanation, the standalone means that the simulation is performed using only the server, not using the GUI. Now, let's watch this video that shows from setting up the DOE analysis in the dialog box to running the DOE analysis. First, click the DOE button to open the DOE dialog box. Then, click the tool button of the DOE to set the number points, the minimum and maximum values of the DOE, and click the Generate button. Click the OK button. Set the rest of the DOE values as before, and finish the setting process. Then, select the DOE method and click the Create Table with the DOE button to generate a DOE table. After that, check the settings for PI and set the end time and step in the Simulation tab. As you see here, the number of trials is 0. But clicking the R button next to it will update the number of trials, the same as the number of cases in the DOE table created earlier. Click the Simulate button, then the simulation will be performed. After the analysis is complete, the DOE results should be reviewed. You can check the analysis results through the result sheet in the DOE dialog box. First, if you see the rightmost columns of the table, you can check the results of the performance indices. The blue highlighted value is the minimum value. The red highlighted value is the maximum value. You can extract the model after applying the PVs of the specified trial. The update current model function automatically applies the PVs of the specified trial to the current model. Create new model is a function to extract a new model after applying the PVs of the specified trial. Now, let me explain the functions that allow the user to check the result through graphs. The first is the DV-PI graphs. These graphs allow you to determine which DV is more sensitive or linear in response. The second is the PI graph. The results of all DOE analysis for the selected performance index can be checked in a single graph. The third is the PI graph. This allows you to check the relationship between performance indices. In this chapter, we will focus on the overview and usage of a simulation manager. First, let me introduce you to the simulation manager. Briefly speaking, Simulation Manager enables running multiple simulations required for DOE simultaneously. Simulation can be performed simultaneously as many as the number of licenses the user has. In addition, using a multi-core processor can significantly reduce the time on DOE with the Simulation Manager. You can open the Simulation Manager dialog box by simply clicking the Simulation Manager button. The details about the Simulation Manager dialog box will be explained later. First, there are necessary steps before running the Simulation Manager. Since the Simulation Manager uses only the server for simulation, you need to create the files necessary for the simulation in advance. The necessary files are RMD file and RSS file. It is possible to automatically export them from the DOE dialog box. Specify the directory to which the files will be exported. Then click the Export Files button. You can see that the folders are now created as many as the number of simulations of the DOE table in the specified directory. The RND and RSS files required for the simulations are created in each folder. Here is the dialog box of the Simulation Manager settings. The RecurDyn server parameter, the server exe file to be used for simulation is specified. However, you don't need to worry about it since it is automatically specified. The next is the base directory. The base directory specified in the DOE dialog box is set as the default, but the user can change it anytime. If the additional DOE simulations are required, click the Add Simulations button to add the simulation cases. This shows the settings and status of each simulation case. This will be explained in detail in the later part. The number of concurrent runs means the possible number of simultaneous runs. The maximum number of concurrent runs must equal to or less than the number of available server licenses. When you click the Start the Simulations button, it launches the simultaneous simulations. Here are more details about the simulation settings and status. You can activate the simulation by checking the Use checkbox. If you uncheck the Use checkbox, that case is ignored and not simulated. And the arrow button under the action row plays a role of running or stopping the model. You can set the simulation's priority under the priority row. The simulations can be set from low to high. If all of them are set to normal, they are processed sequentially. You can check the simulation progress under the progress row. In the elapsed time row, you can check the elapsed time of the simulation. Finally, in the status row, you can check the various simulation status. Here is the list of the various status. The most common status are waiting, failed, and succeed. So far, we have learned an overview of a simulation manager. From now on, let's watch this video showing from the steps before DOE execution to DOE run through the simulation manager. First, click the DOE button and then click the Simulation tab. After setting the base directory and clicking the Export button, you can see that the folders are created automatically. Once the export is complete for our simulation folders, click the Simulation Manager button to open the dialog box. After checking the simulation settings, set the number of concurrent runs. Click the Start the Simulations button to perform the concurrent runs. As you can see it from the Simulation Status section, 5 simulations are running at the same time. Simulation Manager allows the simultaneous simulations of multiple cases faster than the normal DOE. I will now show you how much speed improvement has been achieved by the simultaneous simulations through Simulation Manager compared to the normal DOE. Let me talk about the DOE's speed improvement. To compare the speed, compare the results and analysis time of the normal DOE and the DOE using the Simulation Manager. The goal is to determine how much speed improvement has been achieved by comparing simulation time. Since each PC can have different number of cores, the performance was reviewed on 2 types of PCs. One with 4 cores and the other with 16 cores. The test DOE model is the pinball model with 100 cases shown earlier. In the first test case, a rigid body model was used. Normal DOE is a method in which the simulation is performed sequentially one by one. On the other hand, performing the DOE using Simulation Manager is a method to run several cases simultaneously with multi-cores. In this test, DOE analysis was performed while increasing the number of simultaneous runs from 1 to 10 on the PC1 with 4 cores. DOE analysis is performed several times while changing the number of concurrent runs that I explained earlier. On the PC2 with 16 cores, DOE analysis was performed while increasing the number of simultaneous runs from 1 to 32. Lastly, the performance of the flexible body model will be introduced. Using the PC2 with 16 cores, the results and the total simulation time of the normal DOE are compared with the ones of 5 concurrent runs using Simulation Manager. First, let's look at the simulation results obtained from PC1. The analysis speed results for each simulation are set out in the table. In this table, the first row is the item, and the second row is the total analysis time. The third row is a speed improvement compared to normal DOE. In other words, when the normal DOE time is 1, the numbers in the third row means the multiples of how fast each simultaneous simulation using Simulation Manager took compared to the normal DOE. The second column is the total analysis time of the normal DOE run. From the third column to the eighth shows the results of DOE using Simulation Manager. As you see from the table, 1 run, 2 runs, 3 runs, and 4 runs are gradually getting faster. But from 5 runs and above, there's no big change. This phenomenon can be seen more clearly in the graph of total analysis time. It was confirmed that the analysis speed converges after 5 runs based on the red scale mark. In other words, performing 4 concurrent runs is the most effective, which is equal to the numbers of PC cores. When extracting and comparing the analysis results from 1 run, 3 runs, and 5 runs using Simulation Manager with the normal DOE analysis results, you can see that they are identical. The table you see here shows the results from PC2 with 16 cores. If you see the table, there is a case that is up to about 7 times faster. Performing multiple simulations simultaneously using the Simulation Manager has a significant effect on speed improvement. This phenomenon can be seen more clearly in the graph of total analysis time. It was confirmed that the analysis speed converges after 17 simultaneous simulations on the 16-core PC. In other words, performing 16 runs is most effective, which is equal to the number of PC2's cores. The following are the simulation results of the flexible body model. Ball 2 was converted to a flexible body before simulating it, and the flexible body information on the number of nodes and elements can be found on the right. In this test case, when comparing the analysis speeds, the DOE using Simulation Manager shows a speed performance improvement of about 1.7 times compared to the normal DOE. And when running normal DOE and running DOE using Simulation Manager, both the displacement graph of ball 2 and the contact force graph between ball 1 and ball 2 appear to be identical. As explained earlier, it is recommended to set the number of runs as many as the number of PC cores in Simulation Manager. Here's how to check how many cores your computer has. After running Task Manager, check the number of cores under the Performance tab. Lastly, here's the conclusion. So far, We have reviewed the introduction and usage of DOE and Simulation Manager and the performance improvement using Simulation Manager. In the case of a normal DOE, using GUI makes it very convenient and intuitive to create and modify DOE table. It is easy to review the results and possible to repeat simulations. The Simulation Manager, which allows the DOE simultaneous simulations, can achieve speed improvement significantly. In terms of speed improvement, it is confirmed that up to about 3 times is improved for 4-core PC, up to about 7 times for 16-core PCs. In addition, 1.7 times of speed improvement for a flexible body model has been achieved. By setting the DOE through GUI and performing the DOE simultaneous simulations using Simulation Manager, it is confirmed that a very powerful and fast DOE analysis is possible. Hope that you can use the DOE and Simulation Manager properly to be of great help when working. Please note that the features for simultaneous simulations using Simulation Manager requires the additional server licenses. If you want to use the Simulation Manager for DOE analysis, contact Function Bay or one of our sales agencies of RecurDyn. That's it for today. Thank you for watching and see you soon again.